Today we'll be talking about the arrangement of electrons within an atom. And the general structure goes atom, then energy level, sometimes known as main energy level, or electron shell. Then we have the sublevels, and then the orbitals, and finally the electrons, which I will be representing as E with a minus for the rest of this chapter. So electrons exist within orbitals, which exist within sublevels, which exist within energy levels, or electron shells, which then exist within the atom. The energy level corresponds pretty well to our previous understanding of the atom, which is that we have some neutrons in the middle, and then an electron shell holding 2 electrons, and another electron shell holding 8 electrons, and maybe the third electron shell holding possibly another 8 electrons. So this is probably what you know from secondary school, and each of these shells correspond to one energy level or electron shell. So far, the atom and energy level is exactly what you've learned in secondary school. But we want to delve a little bit deeper into the level of sublevels and orbitals. So each energy level is actually split into different sublevels. And there are 4 different types of sublevels, namely S, P, D, and F. And each different type of sublevel holds a different number of orbitals. And that results in a different number of electrons being stored in that sublevel. So first we have S, and S sublevels hold 1 orbital, and each orbital can hold only 2 electrons. So the S sublevel can hold 2 electrons. The P sublevel can hold 3 orbitals, and as such can hold 6 electrons. The D sublevel holds 5 orbitals and thus holds 10 electrons. And lastly, the F sublevel holds 7 orbitals and 14 electrons. So between the different sublevels, the number of orbitals is always increasing by 2, and the number of electrons is the number of orbitals multiplied by 2. So each electron shell can hold more and more sublevels. So for instance, the first electron shell has one sublevel, the 1s sublevel, which is why in atom diagrams we often see that the first shell only has 2 electrons, right? And the second electron shell will hold the s and the p sublevel, in total giving 8 electrons, which is frequently why we see the second electron shell with 8 electrons. The third electron shell actually does not contain 8 electrons. It can hold much more, just that in secondary school we often see it only containing no more than 8 electrons usually. The third electron shell can actually hold the S and P and D sublevel, giving it a total of 18 possible electrons that it can have. And so on for the fourth and fifth electron shell. Okay, so let's move on to some exam skills, mainly knowing how to draw orbitals. And this is really simple. The s orbital is just a sphere, and the p orbital is a dumbbell shape. And that's all you have to know. Let's talk a little bit more about some extra information which you may find interesting to note. If you recall, the p sublevel holds 3 different orbitals, and these orbitals all have the same dumbbell shape, that sort of infinity looking shape, but they are arranged differently in space. So if you would like to read a little bit further, you'll find out that the p orbitals are actually labeled px, py, and pz orbitals based on the way that they are arranged in space along the x, y, and z axis. So the px orbital would be, you guessed it, aligned along the x-axis. The py orbital would be aligned along the y-axis, and the pz orbital would be aligned along the z-axis. Altogether, this is what the p sublevel looks like. Now we want to make use of our newfound information about sublevels, orbitals, and energy levels to write down electronic configurations. Before we do that, there are a couple of rules that you need to know which govern the electronic configuration. The first rule is called the Aufbau Principle. Now, you don't have to know the names of these rules, you just have to understand them in order to write out the electronic configuration correctly. The Aufbau Principle states that electrons are added from the orbital with low energy to the orbital with high energy. So we add electrons into the lowest energy orbital first. And there's a diagram that you may have seen which will help you to determine which orbital has the lowest energy. So what you do is split a section of your paper into 4 columns and label them S, P, D, and F for each of the 4 different types of sublevels, and then split the rows into 1, 2, 3, and 4. You could go to 5, 6, and 7, but 4 is usually enough. So what we have to do is just fill in the orbitals, taking careful note of what kind of orbitals don't exist. For example, the 1s orbital exists, but the 1p, 1d, and 1f orbitals don't exist. The 2s orbital exists, and so does the 2p orbital, but the 2d and f orbitals do not exist. The 3s, 3p, and 3d orbitals exist, but not 3f. And for the 4th energy level, all 4 of these types of orbitals exist. The next step is to draw some diagonal arrows. So the first arrow goes across 1s, the second arrow goes across where 1p would be and into 2s, the third arrow goes from 1d to 2p to 3s, the fourth arrow will cut through 3s and 4s, fifth arrow through 3d and 4p, and so on. So the way we write out electronic configurations is that we follow these arrows from top to bottom and just follow the general direction of the arrow and see which orbital it cuts through first. So the first arrow cuts through 1s first, so we write down 1s. The second arrow cuts through 2s, so we write down 2s. The third arrow cuts through 2p and then 3s, so we write 2p, 3s. The fourth arrow cuts through 3p and then 4s, so we write that. The fifth arrow cuts through 3d, then 4p. And this is where we usually stop because we rarely see atoms that go beyond, but you could continue to write down the 4d and 4s sublevels if you like. So this is the order of orbitals from low energy to high energy. And it seems pretty straightforward with the exception of the 4s and 3d orbitals. So when we are filling in electrons, we have to fill in the 4s orbital before we fill in the 3d orbital. The next rule we have is the Pauli exclusion principle, which just states that an orbital can hold a maximum of 2 electrons. The reason this happens is that electrons actually have something called spin. This dwells a little bit into the realm of physics and is not in the syllabus, but when electrons are paired, the spin cancels out, which makes them a little bit more stable. So given the Aufbau principle and the Pauli exclusion principle, this is enough to write out the electronic configuration of atoms. This is an important exam skill, and I will give you an example before we try writing out on your own. So let's start with sodium. Sodium has 11 electrons since its atomic number is 11 in the periodic table. So we need to write out enough sublevels to contain all these 11 electrons. So starting from the lowest energy orbital, we have 1s. 1s can hold 2 electrons, so we write 2 to denote this. Then we move on to 2s, which can also hold 2 electrons, and we've settled 4 out of the 11 electrons. Then we have the 2p sublevel, which has 3 orbitals, allowing it to store 6 electrons. So at this point, we have 10 electrons in their orbitals, and we're just left with 1, and that last electron would be in the 3s sublevel. This is the electronic configuration. Specifically, this is the full electronic configuration. There is also something called the condensed electronic configuration. And how you write the condensed electronic configuration is that you look at where your atom is and find the noble gas that is one period above. So sodium is in the third period, which means that we have to look at the noble gas in the second period, and that would be neon. Neon contains 10 electrons, so we just have to give one more extra spot to the next electron, and that would be the 3s, 1 electron. So this is the condensed electronic configuration. So pay attention to what kind of electronic configuration the question is asking for. Next, we have something called the arrow in box diagram. So for the arrow in box diagram, it is just the electronic configuration but presented in a different way. We just draw boxes for each of the orbitals. For example, 1s would have one box for one orbital. Likewise for 2s, and 2p would have 3 boxes. 3s would have 1 box, 3p would have 3 boxes, and so on and so forth. And in the arrow in box diagram, we represent electrons in a half arrow. So it looks like one arrow, but with half of the diagonal line cut out. And this represents 1 electron. If we are pairing up electrons, we draw the same half arrow, but in the opposite direction. And this denotes, remember, the spin, which is part of the Pauli exclusion principle. Electrons have spin and they spin in opposite directions when they are paired up in orbitals. Again, spin is not covered in the syllabus, but you have to draw the arrow in box diagram carefully. And to fill in the arrow in box diagram correctly, we have to consider the Hund's rule. Hund's rule states that when we are filling in a sublevel, each orbital of that one sublevel must be occupied singly, such that each orbital has 1 electron before we start to pair up any electrons. So if we consider the electronic configuration of oxygen, oxygen has 8 electrons. Let's quickly draw the arrow in box diagram. Right, so we have 2 electrons in 1s, 2 electrons in 2s, and 4 electrons to be filled in 2p. According to Hund's law, we have to fill in the electrons singly in each orbital first before we pair up the last electron. So this is correct according to Hund's rule. And this representation of the arrow in box diagram is wrong because it doesn't follow Hund's rule. So now you have all of the tools required to draw out some electronic configurations and arrow in box diagrams. So let's try that out for boron and aluminium. Pause the video here, take a couple of moments to try this question out, and I will show you the answer in a couple of seconds. So boron in total has 5 electrons. So the electronic configuration would start with 1s having 2 electrons, 2s having the other 2 electrons, and the last remaining electron would go to 2p. And this is the full electronic configuration of boron. You could also represent this as helium, 2s2, 2p1 for the condensed electronic configuration. The arrow in box diagram would look like this, with 2 electrons in 1s, 2 electrons in 2s, and 1 electron in the 2p orbital. Taking note that you still have to draw 3 boxes for the 2p sublevel. Aluminium contains 13 electrons, so we have 1s2, 2s2, 2p6, giving us a total of 10 electrons, and then 3s2, and the last remaining electron going into 3p1. And the condensed electronic configuration would be neon, 3s2, 3p1. The arrow in box diagram looks like this. Don't forget to label the sublevels. Now, there are a few exceptions to the Aufbau principle, namely within the transition elements. Let's take a look at chromium. Chromium has 24 electrons according to the periodic table, So take a couple of moments to try and write out the electronic configuration according to the Aufbau principle. And this means filling in the 4s sublevel before we fill in the 3d sublevel. The correct answer is argon 3d4, 4s2. Interestingly though, what we observe is that this is actually wrong. And in real life, we observe argon 3d5, 4s1. This is the correct electronic configuration for chromium, even though it violates the Aufbau principle. And likewise for copper, according to the Aufbau principle, we would expect to see 3d9, 4s2, but instead we observe 3d10, 4s1, again violating the Aufbau principle. So this is an exam question that you need to know. The reason why chromium and copper violate the Aufbau principle is that half-filled and fully filled subshells are more stable. So the 3d5 4s1 electronic configuration is more stable than 3d4 4s2. If you draw the arrow in box diagram, considering 3d4 4s2, we can move one electron over into the 3d orbital, and we have a half-filled 3d orbital here, which is more symmetrical and more stable. Likewise for copper, we have 3d9, 4s2, but if we move that one 4s electron into the half-filled 3d orbital, we will get a fully filled 3d orbital in copper, which is more stable than the 3d9 4s2 electronic configuration. Whereas all of the other transition metal elements like manganese or iron or cobalt have 4s2 and a incompletely filled 3d sublevel. So chromium and copper are very well-known examples, and you have to memorize this. Let's consider the electronic configuration of ions. For anions, we have the addition of electrons, and we add it according to the Aufbau principle from the lower energy orbital to the higher energy orbital. For cations, it is slightly trickier. We remove electrons from the highest energy orbital first. So this is essentially the opposite of the Aufbau principle, with an important exception. For transition metal elements, we remove electrons from the 4s orbital before we remove from the 3d orbital. So let's take a look at the example of iron. Iron has 26 electrons according to the periodic table. Take a couple of moments to write out the electronic configuration of iron. The condensed electronic configuration would be argon 3d6, 4s2. So if we are trying to write out the electronic configuration of the iron 2 plus ion, we remove 2 electrons from the 4s orbital, giving us argon 3d6, since we have removed the 4s orbital. And for the iron 3 plus ion, we have argon, and we are removing 3 electrons. So we take away 2 electrons from the 4s sublevel, and then we remove 1 more electron from the 3d sublevel, leaving us with argon 3d5. Okay, let's take a look at this question, which is the correct electronic configuration of the sulfur 2 minus ion. So take a couple of moments to solve this, and I will provide you with the answer in a couple of seconds. The correct answer is actually option C. So the first thing is I will always pay attention to what I'm trying to find the electronic configuration of. In this case, it's not just sulfur. It's sulfur 2 minus ion, which means I have added 2 electrons. So what I prefer to do is I will write out the electronic configuration of the parent atom first, meaning I will not consider the ion, but just the sulfur atom. So the sulfur atom has 16 electrons, and if you've figured out the electronic configuration correctly, option 1 is the electronic configuration of the sulfur atom. All right, so now I have to add in 2 more electrons. Now B is definitely wrong because I have removed electrons, giving me the sulfur 2 plus ion, which is wrong. C is correct because I've added 2 electrons according to the Aufbau principle. D is wrong because I've added the electrons to the 4s sublevel instead of 3p, which violates the Aufbau principle, making C the correct answer. And that's it on electronic configuration. I hope that I've cleared some of your doubts. If you have any questions, feel free to email me.